When you look up at the night sky, you are seeing light that has traveled across vast distances to reach your eyes. Some of that light left its star decades ago, some hundreds of years ago, some thousands. The stars appear as small points against the darkness, distant and quiet, scattered across the expanse above. They seem so separate from us, so far removed from daily life, yet they are connected to everything around you in ways that are both simple and profound. The atoms that make up your body were not always part of you. They existed long before you were born, long before the Earth itself existed. These atoms were forged inside stars that lived and died billions of years ago, stars that no longer shine but whose material remains, scattered and reformed into new things. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it came from stars. You are made of stardust, and so is everything you touch, everything you see. This is not poetry, though it sounds like it might be. This is simply what happens in the universe, a quiet process that unfolds over incomprehensible stretches of time. Stars are born, they shine for millions or billions of years, and then they release their material back into space. That material drifts through the cosmos, gathering slowly into clouds, condensing into new stars and planets, becoming part of rocks and water and living things. The cycle continues, patient and unhurried. Space itself is mostly empty. Between the stars, there is darkness and silence, a void so vast that light itself takes years to cross it. Yet even in this emptiness, there is substance. Thin clouds of gas and dust drift through the darkness, so diffuse that you could pass your hand through them and feel nothing. These clouds are made of hydrogen and helium, the simplest elements, along with traces of heavier atoms left behind by stars that died long ago. The clouds are cold, just a few degrees above absolute zero, and they move slowly, stirred by gravity and the faint pressure of starlight. Over time, in certain places, these clouds begin to collapse. Gravity pulls the gas and dust together, slowly at first, then faster as more material gathers. The cloud contracts, becoming denser, and as it does, it begins to warm. Deep inside the collapsing cloud, the temperature rises, the pressure builds, and eventually, if the conditions are right, something remarkable happens. The core becomes hot enough and dense enough for hydrogen atoms to fuse together, releasing energy in the process. A star is born. This birth is not sudden or violent, despite what the word born might suggest. It is a gradual process, taking hundreds of thousands or even millions of years from the first stirrings of collapse to the moment when fusion begins. The new star settles into a steady rhythm, burning hydrogen in its core, releasing light and heat that push outward against the inward pull of gravity. This balance is what allows a star to shine steadily for such long periods of time. The outward pressure from fusion matches the inward pull of gravity, and the star remains stable, a glowing sphere of gas suspended in space. Our own Sun is such a star, formed about 4.5 billion years ago from a cloud of gas and dust that was itself enriched with material from earlier stars. The Sun will continue to shine for billions of years more, converting hydrogen into helium in its core, releasing the energy that warms our planet and makes life possible. It is a middle-aged star, neither particularly large nor particularly small, not especially hot or cool. It is ordinary in almost every way, one of hundreds of billions of stars in our galaxy alone. The light from the Sun takes about 8 minutes to reach the Earth. It travels through the vacuum of space at the speed of light, crossing the vast distance between the Sun and our planet in that brief span of time. When you feel the warmth of sunlight on your skin, you are feeling energy that was released in the core of the Sun, energy that took thousands of years to work its way from the core to the surface, and then just minutes to cross space and reach you. The light is gentle, steady, a constant presence during the day, filtered and softened by the atmosphere. Stars come in different sizes and temperatures, and these differences determine how they live and how they die. Small stars, those with less mass than the Sun, burn their fuel slowly and can shine for tens of billions of years or more. They are cool and dim, glowing with a reddish light, and they consume their hydrogen so gradually that even the oldest of them, formed shortly after the universe began, are still shining today. These stars will outlive almost everything else in the cosmos, burning steadily long after larger stars have exhausted their fuel and faded away. Larger stars, those with more mass than the Sun, live faster and brighter. They burn through their hydrogen at a much quicker rate, shining with intense heat and light. A star 10 times the mass of the Sun might last only 10 or 20 million years before it runs out of fuel, a brief lifetime compared to the billions of years a smaller star might enjoy. These massive stars are rare, but they are important, because it is in their cores that heavier elements are created. When a star like the Sun burns hydrogen, it produces helium. For most of the star's life, that is all it does. The helium accumulates in the core, while the outer layers continue to fuse hydrogen. But eventually, the hydrogen in the core runs out. When that happens, the core contracts, heating up, while the outer layers expand and cool. The star swells into a red giant, its surface moving outward, its color shifting from yellow to orange to red. The Sun will do this one day, billions of years from now, growing large enough to engulf the inner planets, its outer layers reaching perhaps as far as the Earth's current orbit. In the compressed, heated core of a red giant, helium begins to fuse, creating carbon and oxygen. This process releases energy, but not as much as hydrogen fusion, and it doesn't last as long. When the helium runs out, smaller stars like the Sun cannot generate enough heat and pressure to fuse carbon or oxygen. The core contracts as much as it can, but there is no more fusion to push back against gravity. The outer layers drift away gently, forming a glowing shell of gas around the remaining core. This shell is called a planetary nebula, though it has nothing to do with planets. It is simply the outer envelope of the star, cast off into space, illuminated by the hot core left behind. The core itself, now exposed, is called a white dwarf. It is small, about the size of the Earth, but incredibly dense. A teaspoon of white dwarf material would weigh tons. The white dwarf no longer undergoes fusion, it simply radiates away the heat it has left, cooling slowly over billions of years. Eventually, it will cool completely, becoming a dark, cold cinder floating through space, though the universe is not yet old enough for any white dwarf to have reached this final state. The gas that was cast off into the planetary nebula, however, does not disappear. It drifts outward, mixing with the interstellar medium, the thin gas and dust that fills the space between stars. This material contains all the elements that were created inside the star during its lifetime, carbon, oxygen, nitrogen, and traces of heavier elements. These atoms join the cosmic clouds, enriching them, adding complexity to what was once just hydrogen and helium. When new stars form from these clouds, they will contain these heavier elements, and so will any planets that form around them. Massive stars follow a different path. When they exhaust their hydrogen, they too become giants, swelling to enormous sizes. But their greater mass allows them to keep going, fusing helium into carbon and oxygen, then carbon into neon and magnesium, then onwards to silicon and sulfur, and finally to iron. Each stage of fusion releases less energy and lasts for a shorter time. A massive star might spend millions of years burning hydrogen, thousands of years burning helium, a few hundred years burning carbon, and only a few days burning silicon. The creation of iron marks the end of the line, because fusing iron requires energy rather than releasing it. When the core fills with iron, fusion stops. Without fusion to provide outward pressure, the core collapses in an instant, falling inward under its own immense gravity. The collapse is so sudden and so violent that it releases more energy in a few seconds than the star has released in its entire lifetime. The core rebounds, sending a shockwave outward through the star, and the star explodes in a supernova, one of the brightest events in the universe. For a brief time, a supernova can outshine an entire galaxy, visible across vast distances of space. But even this explosion, as dramatic as it sounds, happens far away, in the silence of space where there is no air to carry sound. If you were watching from a safe distance, you would see the star brighten suddenly, its light increasing over hours or days, then gradually fading over weeks and months. The explosion sends the star's outer layers racing outward at tremendous speed, but from here, from the quiet darkness of your bedroom, it is just a distant point of light that grows bright and then dims. The supernova scatters the star's material across space, and this material contains all the elements that were created during the star's life and in the explosion itself. Elements heavier than iron, gold, silver, uranium, platinum, are formed during the supernova, in the intense heat and pressure of the explosion. These rare elements, along with all the others, are blown outward into the surrounding space, seeding the interstellar clouds with the building blocks of planets and life. What remains of the star depends on its mass. A very massive star might collapse completely, forming a black hole, a region of space where gravity is so strong that not even light can escape. A slightly less massive star might leave behind a neutron star, an object even denser than a white dwarf, where the matter is compressed so tightly that atoms themselves are crushed, leaving only neutrons packed together. A neutron star might be only a few miles across, yet contain more mass than the Sun. Some neutron stars spin rapidly, sending out beams of radiation as they rotate, and if those beams sweep past the Earth, we detect them as regular pulses. These are called pulsars, and they mark the graves of massive stars, cosmic lighthouses spinning in the darkness. The material ejected by the supernova travels outward, eventually slowing and mixing with the surrounding gas and dust. It forms new clouds, denser in some places than others, enriched with the elements created in the star's core and in its death. These clouds drift through space, gradually spreading out, becoming part of the larger structure of the galaxy. They glow faintly in some wavelengths of light, illuminated by nearby stars or by the energy of the supernova itself, creating beautiful nebulae that we can observe with telescopes, the remnants of stars that died long ago. And then, slowly, the cycle begins again. Gravity stirs these enriched clouds, pulling them together in some regions, starting the process of collapse that will eventually form new stars. These new stars will be different from the ones that came before, because they contain heavier elements. The first stars in the universe, formed just a few 100 million years after the Big Bang, were made only of hydrogen and helium, the elements created in the earliest moments of the universe. Those stars had no carbon, no oxygen, no iron. When they died, they released these heavier elements into space, and the next generation of stars contained them. Each generation enriches the cosmos a little more, adding complexity, creating the conditions necessary for planets and, eventually, for life. Our Sun is a latecomer in this cosmic story, formed from a cloud that had already been enriched by multiple generations of stars. The planets that orbit the Sun, including the Earth, are made from the heavier elements in that cloud, elements that were created inside ancient stars and scattered into space when those stars died. The Earth itself is stardust, gathered together by gravity, compressed and heated and shaped over billions of years into the world we know. The ground beneath your feet, the water in the oceans, the air you breathe, all of it is recycled stellar material. The carbon in every living thing, the silicon in the rocks, the metals that we mine and use, these were all forged in the cores of stars or in the explosions that marked their deaths. When you hold a piece of gold, you are holding atoms that were created in a supernova, perhaps billions of years ago, in a star that existed long before the Sun. The atoms in your body have been part of countless other structures before they became part of you. They have been in stars and in clouds, in rocks and in water, in other living things. They are ancient, far older than the Earth, and when you are gone, they will continue, becoming part of something else. This perspective can make you feel very small, and in a way, you are. The universe is vast beyond comprehension, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. The Earth is a small planet orbiting an ordinary star in an unremarkable corner of one galaxy among countless others. In terms of size and scale, we are insignificant, a tiny speck in an almost infinite expanse. Yet there is another way to see it. You are not separate from the universe, you are part of it. The same processes that created the stars also created you. The atoms in your body are the same atoms that were forged in stellar cores, the same atoms that drifted through space for eons before gathering together to form the Earth and everything on it. You are made of the universe, and the universe is made of you. There is no dividing line, no clear boundary between where you end and where the cosmos begins. You are stardust that has become aware of itself, matter that has organized into a form capable of looking up at the night sky and wondering about its place in the vastness. The universe is old, about 13.8 billion years by current estimates, though such numbers are difficult to grasp. Time on that scale loses meaning. It becomes abstract, a concept rather than something we can truly understand. But the age of the universe means that there has been time for all of this to happen, for the first stars to form and die, for their material to be recycled into new stars and planets, for life to arise on at least one of those planets and perhaps on others. Everything that exists today is the result of processes that have been unfolding for billions of years, slow and patient and inevitable. The stars you see in the night sky are at different distances from the Earth. Some are relatively close, just a few light-years away, while others are thousands of light-years distant. A light-year is the distance light travels in 1 year, which is about 6 trillion miles. Even the nearest star to our Sun, Proxima Centauri, is more than 4 light-years away. The light you see from that star left it more than 4 years ago. You are not seeing the star as it is now, you are seeing it as it was in the past. The farther away a star is, the further back in time you are looking. When you look at a star 1,000 light-years away, you are seeing light that left that star 1,000 years ago. If that star exploded in a supernova yesterday, you would not see the explosion for another 1,000 years. The light has to travel all that distance to reach you, and until it does, you have no way of knowing what has happened to the star. The universe you observe is not the universe as it exists in this moment. It is a patchwork of different times, each star showing you the past, some more distant than others. This means that when you look up at the night sky, you are looking back in time. The stars closest to us show us the recent past, just a few years ago. Stars farther away show us what the universe looked like decades or centuries or millennia ago. And when we look at distant galaxies, millions or billions of light-years away, we are seeing them as they were in the distant past, when the universe was younger, when the Earth did not yet exist. The light from those galaxies has been traveling through space for eons, and it is only now reaching our eyes. Galaxies themselves are vast collections of stars, held together by gravity. Our galaxy, the Milky Way, contains hundreds of billions of stars, along with clouds of gas and dust, and a supermassive black hole at its center. The Milky Way is shaped like a flat disk with spiral arms, and the Sun is located about halfway out from the center, in one of those spiral arms. From our position within the galaxy, we see the rest of the Milky Way as a band of light across the night sky, a river of stars stretching from horizon to horizon. The ancient Greeks called it the Milky Way because it looked like spilled milk across the heavens, a glowing stream of light. Only in the last few centuries have we understood that it is made up of countless individual stars, too distant and too numerous to see separately with the naked eye, blending together into a soft glow. The Milky Way is not alone. It is part of a group of galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and several smaller galaxies. Andromeda is the nearest large galaxy to the Milky Way, about 2.5 million light-years away. It contains roughly 1 trillion stars, more than the Milky Way, and it is slowly moving toward us. In about 4 billion years, Andromeda and the Milky Way will collide, their stars and gas clouds mingling, their shapes distorting as gravity pulls them together. But space is so vast and stars are so far apart that almost none of them will actually collide with each other. The two galaxies will pass through each other like ghosts, their stars rearranged but largely unharmed, and eventually they will merge into a single larger galaxy, a slow cosmic dance that will take hundreds of millions of years to complete. Beyond the Local Group, there are countless other galaxies scattered throughout the universe. Some are spirals like the Milky Way, with elegant arms winding outward from a central bulge. Others are elliptical, smooth and featureless, shaped like elongated spheres. Still others are irregular, with no clear structure, their stars scattered in chaotic patterns. Galaxies cluster together, forming groups and larger clusters, and these clusters are connected by filaments of dark matter and gas, creating a cosmic web that spans the entire universe. Between the filaments are vast voids, regions of space that contain very few galaxies, stretches of emptiness hundreds of millions of light-years across. The universe is expanding. This was discovered less than a century ago, a revelation that changed our understanding of the cosmos. The galaxies are moving away from each other, not because they are traveling through space, but because space itself is expanding, carrying the galaxies along with it. The farther away a galaxy is, the faster it appears to be receding, a relationship that holds true across the observable universe. This expansion means that the universe was smaller in the past, and if you trace it backward far enough, you reach a point where all the matter and energy in the universe was compressed into an incredibly small, hot, dense state. This is what we call the Big Bang, the beginning of the universe as we know it. The Big Bang was not an explosion in space, it was the beginning of space itself and of time. There was no before the Big Bang in any meaningful sense, because time itself began at that moment. The universe has been expanding ever since, cooling as it expands, the matter within it spreading out and forming structures, first simple atoms, then stars, then galaxies, then planets, then life. Everything that exists now emerged from that initial state, shaped by the laws of physics operating over billions of years. In the earliest moments after the Big Bang, the universe was too hot for atoms to exist. Matter existed as a plasma of particles, electrons and quarks flying freely, colliding and separating in the intense heat. As the universe expanded, it cooled, and after about 380,000 years, it became cool enough for electrons to combine with protons, forming the first hydrogen atoms. This moment is called recombination, and it marks the point when the universe became transparent to light. Before this, photons were constantly scattered by free electrons, unable to travel far before being absorbed or deflected. After recombination, the photons could travel freely, and the universe filled with light. This light still exists today, stretched by the expansion of the universe into microwaves, and we can detect it as a faint glow coming from all directions in space. This is the cosmic microwave background, the afterglow of the Big Bang, a snapshot of the universe as it appeared just a few 100,000 years after it began. The first stars formed a few 100 million years after the Big Bang, condensing out of the clouds of hydrogen and helium that filled the early universe. These stars were massive and short-lived, and when they died, they scattered the first heavy elements into space. Over time, more stars formed, more elements were created, and the universe became more complex. Galaxies assembled from smaller structures, pulled together by gravity, and within those galaxies, stars continued to form and die, recycling their material in an ongoing cycle. The Sun and the Solar System formed about 9 billion years after the Big Bang, relatively late in the history of the universe. By that time, the cosmos had already gone through multiple generations of stars, and the clouds of gas and dust were enriched with heavy elements. When the Sun formed, a disk of material surrounded it, and within that disk, particles began to stick together, forming larger and larger clumps. These clumps collided and merged, growing into planetesimals, then into planets. The inner planets, including Earth, are made mostly of rock and metal, the heavier elements that could withstand the heat close to the Sun. The outer planets are larger and made mostly of gas and ice, materials that condensed farther out where it was cooler. The Earth formed from countless collisions, a violent process that took tens of millions of years. The young planet was hot, its surface molten from the energy of impacts and from radioactive decay. Over time, it cooled, and a solid crust formed. Water, delivered by comets and asteroids, accumulated on the surface, forming the oceans. The atmosphere, initially composed of gases released from the interior, gradually changed as life emerged and began to alter the chemistry of the planet. All of this, the rocks, the water, the air, is made from stardust, atoms created in stars and gathered together by gravity into the world we inhabit. Life itself is made of stardust. The elements necessary for life, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, were all created in stars. Carbon, the backbone of all organic molecules, was formed in the cores of red giants. Oxygen, essential for water and for respiration, was created in massive stars and scattered into space when they died. The water in your body, the proteins, the DNA, the complex molecules that allow cells to function, all of these are built from atoms that were once part of stars. Life is a way for the universe to organize itself into complex, self-sustaining patterns, a process that emerged on Earth and may have emerged elsewhere as well. Looking up at the stars, you are seeing the sources of your own existence. Those distant points of light are not separate from you, they are your ancestors in a literal sense. The atoms in your body were created in stars, and when you die, those atoms will return to the Earth, and eventually, over unimaginable spans of time, they may return to space, perhaps to be incorporated into new stars, new planets, new forms of existence. You are part of a cycle that has been ongoing for billions of years and will continue for billions more. The night sky is filled with more than just stars. There are planets, reflecting the light of the sun, moving slowly against the background of stars. There are asteroids and comets, remnants from the formation of the solar system, chunks of rock and ice that orbit the sun in their own paths. There are nebulae, glowing clouds of gas and dust, some illuminated by nearby stars, others dark and visible only because they block the light from stars behind them. There are star clusters, groups of stars born from the same cloud, moving through space together. There are galaxies, so distant that they appear as faint smudges of light, each one containing billions of stars. And there is darkness, the vast empty spaces between the stars, the voids between galaxies. This darkness is not empty, though it appears so. It is filled with light that we cannot see, wavelengths beyond the range of human vision, and with particles and fields that we are only beginning to understand. Dark matter, a mysterious substance that does not emit or absorb light, makes up most of the matter in the universe, and its gravity shapes the large-scale structure of the cosmos. Dark energy, even more mysterious, is causing the expansion of the universe to accelerate, driving galaxies apart at an ever-increasing rate. These phenomena are not well understood, but they remind us that there is much about the universe that we do not yet know, mysteries that remain to be solved. The universe is both familiar and strange. We live within it, made of its substance, governed by its laws, Yet much of it remains beyond our direct experience. We have never traveled to another star, never walked on the surface of a planet outside our solar system, never seen a black hole up close. Our knowledge of the cosmos comes from the light that reaches us, from the signals we detect with telescopes and instruments, from the mathematical models we build to explain what we observe. We are observers, looking out from our small planet into the vastness, trying to understand our place within it. And yet, for all its strangeness, the universe follows patterns. The same laws of physics that govern the falling of an apple on Earth also govern the motion of galaxies. The same forces that shape the atoms in your body also shape the stars. Gravity, electromagnetism, the strong and weak nuclear forces, these operate everywhere, at all times, creating order and structure out of chaos. The universe is comprehensible, at least in part, and this is one of its most remarkable features. We can look at distant stars and know what they are made of, how they shine, how they will die. We can look at ancient light and see the history of the universe unfolding. The cosmos reveals itself to those who look carefully and think deeply. There is a quietness to the universe, a stillness that is difficult to convey. Space is a vacuum. There is no air to carry sound, no medium for vibrations to travel through. The stars shine in silence, the galaxies turn without a whisper. Even the most violent events, supernovae, colliding galaxies, matter falling into black holes, happen without sound, at least in the sense that we understand it. If you could somehow float in space, far from any planet or star, you would hear nothing. The universe would be perfectly silent around you, a profound quiet that is never experienced on Earth, where there is always some background noise, some hum of life or wind or water. This silence is part of what makes the cosmos feel so distant, so removed from everyday experience. We are used to a world of sound and movement, of constant sensation and change. The universe, by contrast, seems timeless and unchanging, the stars fixed in their positions, the galaxies frozen in their distant light. But this is an illusion created by scale and distance. The universe is in constant motion, stars are being born and dying, galaxies are colliding and merging, planets are forming and evolving. It all happens so slowly, on such vast scales of time and space, that from our perspective it appears still. A human lifetime is a fraction of a second in cosmic terms, too brief to see the slow unfolding of stellar evolution or the gradual dance of galaxies. Yet within that stillness, there is a kind of peace. The universe does not hurry. It does not worry or plan or regret. It simply is, unfolding according to the laws of physics, each moment giving rise to the next in an endless chain of cause and effect. Stars will continue to shine, galaxies will continue to turn, and the cosmos will continue to expand, regardless of what happens here on Earth. This can be comforting in its own way, a reminder that we are part of something much larger than ourselves, something that has been here for billions of years and will continue long after we are gone. The atoms in your body are older than the Earth. They have existed for billions of years, cycling through stars and clouds, through rocks and water and living things. They were not always part of you, and they will not always be. They are borrowed, temporarily organized into the pattern that is you, but ultimately they belong to the universe, and they will return to it. This is not something to fear or to mourn. It is simply the way things are, the natural cycle of matter and energy that has been ongoing since the beginning of time. When you breathe, you are inhaling atoms that were once part of stars. When you drink water, you are consuming hydrogen and oxygen that were created in the early universe and in the cores of dying stars. When you eat, you are taking in carbon and nitrogen and other elements that were forged in stellar furnaces and scattered into space billions of years ago. Your connection to the cosmos is not abstract or metaphorical. It is direct and physical. You are made of the same substance as the stars, and you are powered by the same energy, the light of the sun, which itself is stardust burning in the sky. The sun will continue to shine for another 5 billion years or so, slowly converting hydrogen into helium, providing light and warmth to the Earth and the other planets. Eventually, it will exhaust its hydrogen and begin to change, swelling into a red giant, engulfing the inner planets, its outer layers drifting away into space. The core will contract into a white dwarf, slowly cooling over billions of years, and the solar system will become a quiet, dark place, the remnants of the sun and the outer planets orbiting in the cold void. But this is far in the future, so far that it is difficult to imagine. For now, the sun is stable, and life on Earth continues, sustained by the energy of a star. The stars you see in the sky tonight are different from the stars that people saw thousands of years ago, but only slightly. Some stars have moved in their positions, slowly drifting across the sky as they orbit the galaxy. A few stars have died, their light fading, replaced by new stars that have formed elsewhere. But for the most part, the night sky looks much the same as it did to ancient peoples, to the Egyptians and the Greeks and the Chinese, to every human who has ever looked up and wondered. The stars have been a constant presence throughout human history, a source of wonder and mystery, a reminder of the vastness beyond our small world. Different cultures have seen different patterns in the stars, connecting them into constellations, telling stories about them, using them to navigate and to mark the passage of time. The constellations we recognize today are largely based on those of ancient Greece, but every culture has its own way of organizing the stars, its own mythology and meaning. The stars themselves do not form patterns. They are scattered through three-dimensional space, some close, some far, only appearing to be grouped together from our perspective. But the human mind seeks patterns, and so we connect the dots, creating pictures in the sky, finding familiarity in the randomness. The universe is full of such coincidences and illusions. The moon and the sun appear to be the same size in the sky, but this is only because the sun is much larger and much farther away. The moon is about 400 times smaller than the sun, and the sun is about 400 times farther from Earth, so they appear the same size from our perspective. This is a coincidence, a lucky alignment that allows us to experience total solar eclipses, when the moon passes in front of the sun and blocks its light completely, revealing the sun's outer atmosphere, the corona, glowing softly around the dark circle of the moon. This alignment is temporary. The moon is slowly moving away from the Earth, and in the distant future, it will be too far away to completely cover the sun, and total solar eclipses will no longer occur. The moon itself is made of stardust, formed from the debris of a giant impact early in the Earth's history, when a Mars-sized object collided with the young planet. The impact threw material into orbit around the Earth, and this material gradually coalesced into the moon. The moon has no atmosphere, no water, no life. Its surface is covered in craters, the scars of billions of years of impacts, and its rocks are old, some dating back more than 4 billion years to the earliest days of the solar system. The Moon is a quiet, desolate place, but it is also beautiful in its starkness, a reminder of the violence and chaos of the early solar system, now stilled and settled. The Earth, by contrast, is alive and dynamic. Plate tectonics reshapes the surface, volcanoes erupt, mountains rise and erode, rivers carve valleys, and life spreads across the land and sea. The atmosphere shifts and swirls, clouds form and dissipate, weather patterns move across the globe. The Earth is in constant change, a restless, evolving world, yet all of this activity is powered by stardust, by the energy of the Sun and by the heat trapped within the planet from its formation and from radioactive decay. The rocks beneath your feet are made of minerals, which are made of atoms, which were created in stars. The soil is a mixture of weathered rock and organic matter, the remains of living things that have died and decayed, returning their atoms to the earth. The water in the oceans, in the rivers, in the clouds, is made of hydrogen and oxygen, elements created in the Big Bang and in stars, combined into molecules that cover most of the planet's surface. The air is made of nitrogen and oxygen, with traces of other gases, all of them created in stars and released into space, eventually finding their way to Earth and becoming part of the atmosphere. Everything around you, everything you touch and see and breathe, is stardust, recycled and reformed countless times over billions of years. When you die, the atoms that make up your body will return to the earth. Some will be buried, becoming part of the soil. Some will be cremated, released into the air as gases and ash. But the atoms themselves will not be destroyed. They will continue to exist, joining the cycle, becoming part of other things, plants, animals, rocks, water. And eventually, over timescales so long that they are almost meaningless, some of those atoms might leave the Earth entirely, carried away into space by solar wind or by the eventual death of the Sun, and they might join the interstellar clouds once again, drifting through the galaxy, waiting to be incorporated into new stars, new planets, new forms of existence. The universe is patient. It does not rush. Stars take millions of years to form, billions of years to shine, and then they die and their material is recycled over and over. The cosmos has been doing this for nearly 14 billion years, and it will continue for trillions of years more, until the last stars burn out and the universe becomes a cold, dark place, filled with the remnants of dead stars and the faint glow of radiation stretched by the expansion of space. But that is unimaginably far in the future, so far that it is not worth worrying about. For now, the universe is filled with light and life and possibility. You are here, now, made of stardust, aware and alive, able to look up at the night sky and understand, at least in part, what you are seeing. You are the universe looking at itself, matter become conscious, a temporary pattern of atoms that can think and feel and wonder. This is a rare and precious thing, as far as we know. Life may exist elsewhere in the cosmos, on other planets orbiting other stars, but we have not yet found it. For now, we are alone, or at least we appear to be, isolated on a small planet, the only place in the universe where we know for certain that life exists. But even in our isolation, we are connected. The light from distant stars reaches us, crossing vast gulfs of space and time, bringing information about the universe. The atoms in our bodies link us to the cosmos, a shared substance that makes us part of the whole. And the laws of physics that govern the stars also govern us, binding everything together in a coherent, understandable framework. We are not separate from the universe, we are an expression of it, a way for the cosmos to experience itself. The night is quiet. The stars shine softly, scattered across the darkness, each one a distant sun, each one a furnace where elements are forged. The light that reaches your eyes left those stars years or centuries or millennia ago, traveling through the void, through the emptiness, until it finally arrives here, now, to be absorbed by your retina, converted into signals, interpreted by your brain. You are seeing the past, looking back in time, witnessing the universe as it was, not as it is. And somewhere, out there, on a planet orbiting a distant star, perhaps there is someone else looking up at their own night sky, seeing their own stars, wondering about the cosmos, asking the same questions. Or perhaps there is not, and we are alone, the only conscious observers in all the vastness. Either way, the universe continues, indifferent and sublime, a place of beauty and terror, of light and darkness, of matter and energy, all of it stardust, all of it ancient, all of it connected. The darkness between the stars is not empty. It is filled with possibility, with potential, with the seeds of future stars and planets and perhaps future life. The universe is not finished. It is still evolving, still changing, still creating. New stars are forming even now, in clouds of gas and dust scattered throughout the galaxy. New planets are condensing around those stars, new worlds that might one day harbor life, new places where the universe can become aware of itself. But for now, here, tonight, you are part of that awareness. You are stardust that wonders, matter that dreams, atoms organized into a form that can look up at the sky and feel awe, and curiosity, and a deep, quiet sense of connection to everything that is. The stars will continue to shine, long after you are gone. They will burn their fuel, create their elements, and eventually release their material back into space, continuing the cycle that has been ongoing for billions of years. And some of that material, some of those atoms, might one day become part of another conscious being, another observer looking up at another sky, feeling the same sense of wonder and connection. You are made of stars. You are the universe experiencing itself. And as you drift toward sleep, surrounded by the darkness, you are floating in the same cosmic sea that holds the stars, made of the same substance, governed by the same forces, part of the same ancient, ongoing story. The universe is vast and old and mostly empty, but it is also full of light, full of beauty, full of meaning that we create by observing it, by understanding it, by being part of it. And so the stars shine on, patient and constant, scattered across the darkness, each one a beacon, each one a reminder that you are not separate from the cosmos, but woven into its fabric, made of its substance, part of its long, slow unfolding. The night deepens. The stars will slowly overhead, their positions shifting as the Earth turns. You are spinning through space on the surface of a planet, orbiting a star, which itself is orbiting the center of a galaxy, which is moving through the universe along with billions of other galaxies. Everything is in motion, yet from here it seems still, peaceful, timeless. You close your eyes, and the starlight continues to fall, traveling through space, through time, through the darkness, carrying the story of the universe written in wavelengths of light, in patterns of radiation, in the gentle whisper of photons that have journeyed for years or centuries to reach this moment, this place, this small planet where life has emerged and consciousness has arisen and questions are asked about the nature of existence. And the answer, simple and profound, is this: you are stardust, and you are home. The cosmos surrounds you, holds you, contains you. You are part of it, and it is part of you, and there is no separation, no boundary, no division between the self and the universe. You are a wave in the cosmic ocean, a temporary pattern that will eventually dissolve back into the whole. But for now you are here, alive, aware, made of ancient atoms, illuminated by the light of stars, breathing the air of a planet that circles a sun in a galaxy that drifts through the endless expanse of space. Sleep comes slowly, gently, like the falling of starlight, and as consciousness fades, the universe remains, patient and vast, continuing its slow dance through time, indifferent and magnificent, a place of infinite mystery and quiet beauty, where stars are born and die, where matter becomes life, becomes consciousness, becomes wonder, and where all of it, all of us, all of everything, is made of the same substance, the same stardust, scattered and gathered and scattered again, in an endless cycle that has no beginning and no end, only the eternal present, the moment that is always now, always here, always part of the vast, silent, luminous whole. And in that wholeness, in that vastness, in that silence, there is peace. The stars continue to shine. The universe continues to be. And you, made of stardust, drift into sleep, floating in the cosmic sea, part of everything, separate from nothing, home.